Okay, so welcome to the seminar today. We have the great pleasure today of having Philippe Lacomme, de l'Université de Clermont-Ferrand, visiting here for some days. And then we immediately enrolled him for a seminar. We will talk about some joint project on scheduling plus routing integration. So I think the scene is yours. Okay.
Thank you very much. Thank you very much.
Okay.
Thank you for this introduction. Well, this presentation will not focus on routing, but I will try to define some challenging trends, including both scheduling and routing, trying to define some problems. So, why this kind of definition is of interest? It is because we have two community of researchers who are working on scheduling problem, and a second community of routing. And in these two communities, we can find some very interesting research. For example, in scheduling community, we have many publications which address scheduling with transportation. Not, as I say, transportation, and not routing. And in the second community of the routing, we have many variable algorithms to efficiently solve some routing problem, including, for example, the terrain ride or any pickup and delivery problem, or maybe some extension of vehicle routing. So, in fact, my presentation, which concern both routing and scheduling, and first I will try to define what are the problems which are investigated in scheduling with transport. In this kind of topic, we have many exchanges with several researchers. On work on scheduling, we have many discussion and exchange with researchers at the labs. On scheduling with extra constraint with my PhD student, finally. And for problems which remain in the supply chain management with Daniel. So the first question is, we found the words transportation and scheduling. And the first question can be, what are the research topics in transportation for scheduling? In scheduling, in fact, we have numerous efficient methods to solve disjunctive problem. I mean that in scheduling, we have a set of jobs to schedule. And a set of jobs is commonly defined by another set of operation or activity. And one activity has a duration. Like in this example, we have a job 1, which is assumed to be processed on machine 1 for 10 units of time. After on machine 2 for 10 units of time. And after on machine 3 for 100 units of time. And to obtain a solution in scheduling, we have to solve the disjunction on operation. So to have a solution, we have to construct a graph which modelizes the problem, to show the disjunction for the machine, and next to evaluate the graph to obtain the earliest starting time of operation. Of course, the problem is how to solve because there are many possibilities to obtain an oriented disjunctive graph, and many of these graphs are inconsistent because they can't have cycle. So there exists efficient approach which take advantage of some indirect representation of solution, like we have geometric in routing we have a direct representation in scheduling. So, what we can find in scheduling? So, we have the possibility to modelize the scheduling problem using a graph. In this graph, we have two kinds of arc. We have arc which modelize precedent constraint between operations, of course. And we can have also extra information, including, for example, maximal time lag, delay between two operations, or why not, minimal time lag. To obtain a solution, the first decision consists in defining the order in which operations on similar machines have to be processed. For example, for machine 1, in this solution, we have first the job 1, second the job 2, and last the job 3. So the number of possibilities is very high, of course, and when the disjunction have been added into the graph, it is required to use the longest path algorithm to obtain the earliest starting time of all the operations in this graph. Okay. So a solution of the scheduling problem is a graph where this earliest starting time has been computed. In scheduling program, we obtain after the possibility to have a Gantt chart where we have all the operations in a graphical and friendly way to be analyzed. For example, in this example, we can see that we have a job 1 on machine 1, which finishes at 10, and which starts at 10 on machine 2, and so on. In this trend of research, many extensions of scheduling problems have been addressed. And the first trend of research are research denoted scheduling with transportation constraint. There are many publications, including, for example, Oring and so on, which define extra way to include the transportation into this kind of graph and to evaluate this graph. The challenging problem consists in computing a transport solution with the proper coordination between the loading and unloading movement of truck or of robots. For example, in this Gantt chart, we have a first loaded move of one vehicle. We can imagine that this is a truck or any robot. An empty move from the machine 2 to the machine 1, where the second job is loaded, and next, a loaded move from machine 1 to machine 2, and so on. So, a solution of the scheduling and transport is a solution where we have both scheduled the operation, and second, the empty and loaded move of the robot, or the robot, or one robot, two robots, there's no problem. And we can note that in this solution, we can evaluate easily that at some moment the robot is waiting or some jobs are in the buffer of one machine. How is it possible to include the transport constraint in the scheduling modelization? The basic way consists in updating the graph. In the graph, we have first included only the operation, the machine operation. It is possible to include a second set of nodes which modelize the transport constraint. If we have only one robot with capacity 1, which is the most common problem addressed, the only work consists in adding a new set of nodes and to put the correct value on this arc to modelize the loaded move of the robot. For example, if we consider this instance, we have here data very similar to the data available for the job. A set of job, a set of machine, and we have processing time on each machine. We have here a matrix of transportation time. We can assume that for the loading and unloading move, the time are equal without loss of generality. When we construct the graph, we will have two sets of nodes, the job of the machine operation, the job of the transport operation. In a similar way, that's the way we use for the scheduling problem, we have to determine the order of the transport operation. So you have the disjunction of machine to solve, and you have second, the disjunction of the transport operation. In this graph, when you execute a longest path algorithm, you have the earliest starting time of all the operations. For example, we have this machine operation, which can start at 116, and we have here a transport operation. And the next transport operation is to move the loading move from machine 0 to machine 3. So we can see that using this disjunctive graph with some extra extension, it is possible to include some consideration coming from the routing. Not exactly routing in the sense we use commonly, but in fact transport. Okay. If we have one robot, we have a specific modelization, but it is interesting to remark that this modelization can be not easily, but it is possible to extend this modelization for one or two robots. If we have more than one vehicle, one robot, we have a new problem to solve because we have to assign one vehicle to one transport operation. And if we assume that the capacity of the vehicle is not only one, but why not two, we need to make a distinction between the loading operation, where the job is loading into the vehicle, and the unloading operation, where the job is unloading from the vehicle to the machine. For example, here we have the job 1, which is loaded on vehicle 1. The vehicle 1 make an loaded move from machine 1 to machine 1, in fact duration 0. And a second job is loaded. Next, the robot moves from machine 1 to machine 3, and we have here a delivery of the job 2. So we have in some way here a route or tree where we have pick-up, delivery. A kind of routing which is included into the graph. Okay. And of course, if we compute the earliest starting time of the operation, we can obtain a Gantt which represents the machine operation which have been scheduled. And in each machine operation, you have a delay required to move one job from one location to another location. Here, we can find that the job 1 achieved is processed at 10. We have the robot 1 or vehicle 1 which move from the current position machine 1 to the machine 1. In fact, the vehicle weight. And the second job is loaded. Okay? For this remarks. But it is important to note that in this kind of modelization, we have always used a longest path algorithm to evaluate the graph. It means that we have already computed a solution where the operation, the machine operation, and the transport operation are left shift. It is not very important for the scheduling point of view because the only problem which is addressed here is to know if we can compute a transport problem which is compliant with the scheduling operation. Okay. But we can remark, of course, that in this kind of graph, we could easily measure some extra criteria, and not only the max span, I mean the earliest finish time of the last operation on the last machine. Okay. But to the best of my knowledge, in the scheduling and transportation problem, the problem is only to minimize the max span and to be sure that we can compute a solution of the transportation problem. In this kind of problem, we can find some specific instances, and just have a look in the, on the web to find many publications, and all these publications take advantages of such kind of modelization. Quite different depending on the extension, but very similar to the presentation of the problem I achieved here. We can note also that the instances which are used in this kind of research come from the scheduling and come from sometimes from the flexible manufacturing system. So it is instance which not a very large number of machines and with a number of robots which vary from 1 to 2 and with a capacity strongly limited. Okay. We have not to solve any problem, extra problem of routing, bin packing and so on to be sure that the product can be put in the vehicle and so on. Okay, it is by the transport. So, considering this remark, we can note that we can do several research in this topic. The first one could be trying to define a new way in evaluating the graph. Okay? Because we have always evaluation at the earliest starting time using the longest path algorithm, we could try to find a new way to assign a starting time to the transport operation. It could be interesting to investigate this way. We can remark that to make such research, we can take advantages that in the graph we have a routing problem which is very close to a pickup and delivery problem. Because each time we have to transport a job from one position to the next one, of course we cannot pick the job before he has achieved its process. And it is necessary to deliver the job before he starts the next operation. However, we can note that probably it is difficult to include in this graph some well-known algorithm coming from the pickup and delivery, because the routing problem is included in the graph. And for each transport operation, you have, unfortunately, a machine operation which is next scheduled. So if we change the date of one transport operation, we must be very careful to the consequence for the graph and for the next one. But it is possible to make this. To give you an idea, if you look at this graph, in this position, you can see that we have a transport operation which is assumed to be at 34. And you can see that the machine operation has been scheduled at 34, at the earliest possible starting time. And the robot arrived at 38. And here we have a waiting time on the machine 2. It means that one job has been delivered at 38, and that the machines process the job at 49. If we do not add any extra consideration of the buffer, there is no problem, because you can wait on a machine 1 and machine 2 without any damage for the only criteria which is addressed. I mean the next one. But if we imagine that on the buffer you have some financial cost or some extra consideration, like we have on the DAR, for example, where we have for objective to minimize the total reading time, the total waiting time, this point must be carefully analyzed. How to define this early start. The second strength of remark is that for some scheduling problem, we can have some disjunctive modelization, but we can have also some extra modelization, which could be very interesting for researchers coming from the routing, because in the resolution scheme, we can find some noticeable approach. We could be of some help trying to include routine consideration in the scheduling problem. I mean, for example, the RCPSP, okay, where we have a flow modelization. And the third strand we investigate with Daniel is about scheduling and not transport, but routing. I mean that we could consider the transport not only to be a check of feasibility as regards earlier starting time of machine operation, but as an operation for which we could have some more sophisticated objective, including, for example, the remark of Cordo and Laporte in their specific algorithm. Okay. And if we can achieve this goal, we can try to solve some more complex system coming from supply chain optimization. In supply chain optimization, we have a set of manufacturer, of supplier, of retailer, and the supply chain can be partially modelized as a scheduling problem with precedence constraint between batches or lots. So, in fact, if we have the objective trying to promote some efficient approach for this kind of problem, we have a more complex problem to solve. Not a transport problem, but a routing one. Because to have a model efficient for supply chain optimization, we must consider the size of batches we have to move from one position to a second position. So the problem is not to find a trip or route for one vehicle, one robot, but to be sure that the batches can be put in the same vehicle and so on. So we have a more complex routing problem and not only transport problem. And in this trend of research, we have publications which are defined in the vast majority of time as supply chain optimization in the title, not in scheduling, not in routing, but more in supply chain optimization, and which are, in the vast majority of time, limited to more basic scheduling problem with one machine or several machines in specific configuration. I think that the problem to solve is now a routing one and not a transportation one. The difference is very important because in the transport problem, we have solved the graph. I try to convince you it is possible. I hope I will succeed. We have only computed the earliest starting time of one transport operation. But we know that for a routing problem, it is more complicated. We have to define exactly the departure time of one vehicle. And of course, we have to define the delivery time. To define also the processing time. And we have to evaluate some extra constraints, for example, the total riding time, the total waiting time. And these criteria depend of all the variables of the routing problem. So it is not the same problem as the transportation problem. For example, imagine that we have a supply chain which can be defined using only 3 jobs. We have 3 jobs and we have a batch size, and why not a lot size. In a similar way in the scheduling, we can assume that we have a sequence of operation on different company location, in fact, machine for a scheduling point of view. Okay? Depending on the lot size, we have a sub-job, a lot size, and a set of operation. Okay. When we search for a solution, we have to find a solution of the scheduling problem, of course, for all lot, not for the initial job, for all sub-jobs, which means that we have a problem of great size. And we have to solve the routing problem, considering, of course, the size of the lot size, which is not a so easy problem to solve. Even if we do not address some geometrical consideration, the problem will be very common later on. In this kind of modelization, the solution of the routing we are looking for is a pickup and delivery problem with time windows. So we have to compute a routing solution where we define the time at which the vehicle leaves the depot, reach a machine node, the time he will wait in front of the machine, and the departure time, considering the time windows which come from the scheduling problem. Okay. Note that it is not exactly the kind of problem we found on literature on routing. Because here we have some very specific time windows. For pickup node, we do not have a limitation of the upper bound for the time windows. And for delivery time, we have a time windows with minus infinite and with a limit on the upper bound. Okay. So to solve this problem, we try to promote with Daniel a solution we can be denoted divide and conquer. Why? Because it seems possible to imagine to solve the scheduling problem first. Okay. And to solve the scheduling problem, we can use similar approach as approach for the job shop, or job shop with the disjunctive graph, in which we could include some extra time lag between operations. Including extra time lag between operations does not change the problem. If it will be maximal time lag, the problem changes, but not for the minimal time lag. It is just some extra delay between operations. So it is possible to imagine to have a disjunctive graph which modelizes the scheduling problem, to analyze the time windows which come from the scheduling, and to use these time windows as constraint in the routing one. So we investigate an algorithm which could be composed of 2 steps. The first step, solve first the scheduling problem. Analyze the time windows. And create second a routing problem in which the time windows are constrained. And in the routing step, we must check if it is possible to compute a routing solution which would be compliant with the constraint coming from the scheduling. If not, we have one solution, and the solution consists in increasing the minimal delay between the operations, the minimal time lag. And of course, one word solution exists. We hope that it is possible, of course, to analyze the routine and to define which minimal time lag, which are included in the scheduling, must be increased. Okay. And the process can be iterative as long as we obtain a scheduling solution, a routing solution, which is compliant with the time windows. And after, we need a meta heuristic on some extensions to investigate the search space. And the search space can be considered as the set of all Biarritz vector. I mean, the object, which is equivalent to the geometry in the routing, we have used to create the disjunction between machine and next to solve the routing. Which is important in this point of view, is that we have two sub-problems, the scheduling and the routing. And in the routing one, it is easy to remark that we can use one algorithm, every algorithm previously published for the pickup and delivery with time windows. So it means that we could give to the solution the characteristic we want they have. Not only to check if, okay, the transportation, the robot can move correctly, the vehicle is at the right time, at the right place, but if several solutions exist, we can check the solution we are interested in. So, to sum up this idea, we have a set of Biarritz vectors, which is the set of indirect representation of solutions, like geometry and routing. One Biarritz vector leads to a disjunctive graph, in which we compute the earliest starting time of operation. For one disjunctive graph, we have a set of time windows constraints, which are used in the routing step to search for a solution of the routing. Of course, we are especially interested by a solution for the routing which is very, very time efficient, because this trend will be included next into a meta heuristic or more complicated algorithm. Okay? We first solve the routing using the one algorithm, and we check if violation occurs in the time windows. If some violation occurs, we iterate. So we insert into the disjunctive graph some extra delay. Okay. We re-evaluate the graph. We check again the routing, and so on. As long as violation occurs. Of course, for time efficiency consideration, we can some extra condition to stop the process if we can have the proof that it is not a good solution. Okay. So, what we can have like algorithm. I will not read for you the algorithm, it is not very interesting, but just to explain that. The key point of the algorithm is the evaluation method. And we will have an evaluation method which is composed, in fact, of two parts. The first part consists in first evaluate the initial scheduling graph. The first disjunctive graph where no minimal time lag have been included. Note that we could add some lower bound for the minimal time lag. We could next search for a solution for the routing, and here we have a loop. As long as duration appears in the routing, we will iterate by adding a new minimal time lag into the graph. When the procedure stops, two possibilities. And the procedure stops with a feasible solution, or with unfeasible one. which is possible if we add some extra constraint to stop the procedure. We can imagine that after 5 or 6 iterations, we put the solution into the garbage and we try the next one because the solution is not of interest. So, to give you an illustration, we have a scheduling problem with a graph, non-oriented. We create an oriented disjunctive graph, and we compute here the earliest starting time of the operation. After, we check all of earliest starting time and all earliest finish time. And we will have, for each job, a set of time windows. For example, for the job 1, here, we have a pickup dot. It means that the job cannot be picked up before 5, at every time greater than 5. And we have next a delivery node. It means that considering the scheduling solution, the job must be delivered before 30. So we have here the input data of the routine. For the routine, we have to create a solution composed of thread. I mean the sequence of pickup delivery node, considering, of course, the capacity of vehicle. But for solving this problem, we have many algorithms available. We can search for a very basic solution, or we can use some very sophisticated approach, including the Cordo and Laporte algorithm. This algorithm which permits to find a solution in which we minimize the first criteria, and second, a set of second criteria. For example, the total idling time for a customer, which could be of great interest in a supply chain optimization. And at the end of this process, we need to imagine, of course, that this evaluation lead to a local search algorithm and to a meta-heuristic algorithm. And for these 2 points, we have plenty of approaches available. The first one consists in looking at the graph where we have a longest path. So we have the set of critical operations. So we can use the classical job shop-like approach to change the machine disjunction. The only complication leads on the minimal timeline included in the graph. A solution at the end of the process is the earliest starting time of the operation and all the date which have been computed for the routine. Note that I have included here the delivery time, the beginning of service, the departure time, the waiting time, and so on. Okay. Which is not the same problem as the transportation we have speak when we now talk about scheduling and transportation. Okay. And in this kind of routing solution, for example, we have here a constraint duration and another one and another one. It means that the date at which the vehicle reaches the node is greater than the upper bound of the time windows. If we look at the solution, we have a solution in which, for the scheduling problem, we will have a Gantt where extra delay between operations. This delay are required to find a solution to move one job from one position to another position, considering the constraint of the routing, the capacity of vehicle, the speed of the vehicle, and many extra constraints we could include in the routing. So, in this presentation, I would like to present you some idea of scheduling and transport, and next scheduling and routing. It seems to me that this is of great interest to solve this kind of problem. And we have many publications in routing and many publications in scheduling. And it seems that some specific problem could be efficiently solved if we could merge the research in scheduling and the research in routing. It is not a straightforward problem to solve this kind of problem, because as I stressed to you, if we try to work directly on the disjunctive graph, we will have many difficulties. But here, with Daniele, we have found a way which seems to be interesting. Of course, in this research we try to promote, we have some difficulties. We have to find a good way to manage efficiently the scheduling and the routing, to have a proper coordination. Okay? But according to me, this kind of research in scheduling with routing could be of great interest and quite different than research we have made during several years for routing. I hope I convince you there is some interest in studying this kind of problem.
Thank you very much. Is there any question from the audience or from remote?
We should check from.
In practice, you could use the composition idea also to present, to develop exact algorithms. I don't know if this is reasonable for the instances that you deal with, but you solve exactly the scheduling and then you have to solve exactly the PRP with time windows, and then that will produce a counter.
Yes, of course. We try to achieve this goal. Yes, we try.
No, it is. That's clearly true.
Yes.
That's
yes.
food for you.
No. Go ahead.
But it could be easy, for example, very interesting, to solve the routing problem with some geometrical consideration of items which could be put in the vehicle. And such extension, according to me, would be very difficult to include in the disjunctive graph of the scheduling, which is limited to vehicle with capacity 1 or 2, with no difficulties for the routing, which is called transport, not routing. It's quite different.
Okay. Any